Hi again, everyone. This is part one of the lab entitled Interference and Diffraction. And in this lab, the part one will have to do with the double slit experiment. What is a double slit experiment? Basically, it's a situation where you have a light source that produces light waves, and the light waves are forced through two small apertures, two small holes on an obstacle or a screen. And when they go through those apertures, they behave as though you had two sources of light. So if you can see here, this is my source. This is one of my apertures. This is the other aperture. And the distance between the two apertures is labeled lowercase d. All right? The distance between the two apertures is labeled lowercase d. And so when the light reaches the apertures, this aperture here and this one here behave as though there were two distinct sources of light. This light source has a unique wavelength which is known as a monochromatic wave. So because it's monochromatic, when it gets here, you have two sources having the same kind of light, two distinct sources having the same kind of light separated by a distance d. When the waves go out through the small apertures, they turn to burst out. All right, and as they burst out, they interact, they interfere, either constructively or destructively. As you would have found in your notes, constructive interference means they produce a very bright light signal, which is just the sum of the amplitude. Destructive interference means they cancel out and they produce a dark spot. The bright spots are labeled here by the red circles that you can see here. This is the first and the brightest of all the circle. This is called the central maximum. It is the brightest fringe produced by two signals. After that, you have other bright fringes that are produced above and below the central maximum. You have one that is called N1. There's another N1 below. If our board was bigger, you will have an N2 above, an N2 below, and the bright fringes will continue. All right? Now, the distance from your slits to the screen is going to be called uppercase L. We're going to call this ray 1, the ray coming out from the first source, and ray 2, R2, the ray coming out from the second source. What we find out easily here is that ray 1 and ray 2 will interfere to produce a central maxima at N0, a bright spot at N1, another bright spot at N1 right below the central maxima, and that the distance between the center of the central maxima and the center of the next bright fringe is a distance y, lowercase y. Likewise, the distance between the central maxima and the lower bright fringe n equal 1 is another distance y. In between the bright fringes, you have the dark spots, the dark fringes, okay? All right? So in between the bright fringes, you have the dark fringes. So if I was to add the next bright fringe to my system, it will look, so let me take away the word screen. Now that you know this is the screen, I can wipe that out. We'll have had another bright fringe here, which will be equal to N equal 2. Then another white wave diffraction, another bright fringe here, which would have been N equal 2 as well, okay? And it goes on and on. Now back to business here. So there's an angle that is formed between a straight line going from the slit to the screen and ray 1. That angle is called theta. Likewise, there is an angle formed, well, before I talk of the second of that same angle, you will realize that if I focus on N1, the distance covered by R1 to get to N1 is shorter than the distance covered by R2 to get to N1. And the reason is simply that those two rays come from two different sources that are a distance d apart. Let me make some slight improvement to this drawing so you can clearly see what's happening here. I'm going to wipe out R2 and make it a little bit more reasonable. By that I mean, I'm going to make sure R2 coincides with R1 here, so you know it's an interference. You see the meet there, and there's an interference to produce that bright spot. And so back to what we heard, this is my R2. The distance, the displacement difference, the difference in distance covered between R1 and R2 is this piece here. Let me get the green marker here. This distance here is the difference in distance covered by R2 with respect to R1. R1 is closer to N1 on top, and so covers a shorter distance to get to N1. R2, which is a distance D from R2, which comes from a source, which is a distance D from the source from which R1 came, covers a longer distance to get to N1. So there's a difference between the distance covered by ray 1 and the distance covered by ray 2. And that difference in displacement is this chunk of distance. We should call that distance S. All right? We should call that distance S. Now, from geometry, this angle theta also reflects itself here as theta. Okay? So the angle between the difference in distance of R1 and R2 and the length of this aperture here, because you kind of see a triangle here, don't you? There's one triangle, that the red line, the purple line, then this straight line that corresponds to the slit. They form a triangle for which the angle at the tip of that triangle is also theta, like the angle between R1 and the straight line. You can prove that using geometry. Basically, you look at this angle and this purple line and the red line, you have 90. If this is theta, and then you do a rotation, this will bring theta as well here. I'm not going to go into details with the angle movement because one, we don't have time, and we have a very limited board surface for me to do the mathematics here. But I'll give you the essential formula that you can use. I just want you to have a visual of what is really happening. So how do we go about to solve and find out what this distance is? We want to know the distance between the two apertures of a double slit. How do we find that? So the way we go about to solve that is as follows. We have an expression generally for a double slit experiment, we have n lambda equals to d sine theta. This is for the double slit experiment. We're dealing with the bright fringe at n equal 1. So when n equal 1, this becomes lambda equal d sine of theta. All right, so what is sine of theta? If I look at theta right here, or right here, sine of theta, which is my opposite of my hypotenuse, should be s over lowercase d. Am I right about that? Sine of theta should be the opposite over the hypotenuse. All right. What about tan of theta? I will tell you why I'm looking at tan of theta. What do you think tan of theta should be? Tan says it's opposite over adjacent, right? So let me, initially, for sine of theta, I use the red theta, this theta right here. For tan of theta, I will use the green theta right here. So opposite over adjacent will be this distance from the center. It will be the distance from the center here of this fringe to that fringe. So my tan of theta should be y opposite over my adjacent, which is the distance from the slit to the string, L. Now, mind you, this drawing is not perfect, right? Ideally, this line, I should have drawn it in such a way that it lands at the center of N0. I can do that all over, but I don't want to mess the drawing, okay? So this green line normally lies at the center of N0, and this R1 lands at the center of N1. What that means is that the opposite distance for theta will be the distance from the center of N1 of N equals 0 to the center of N equals 1, which we have shown is y. So tan of theta should be y over L. Geometry. Now, for this experiment, we assume we are dealing with very small angles. What does small angle means? It means the sine of theta is approximately the tangent of theta. Alright? That's the approximation we're going to use here. Which means, in this expression, right? So, which means my sine of theta must not be s over d. I don't know d. Why should I make my sine of theta d, right? Instead of saying my sine of theta is s over d, I can use the tan of theta, because for small angle sine of theta, let me write this a little bit bigger so it gets into. So for very small angles, the sine is approximately equal to the tangent. This implies this expression sine of theta equals to s over d can be replaced by sine of theta equals to y over L. Remember, y over L was a tangent, but since sine and tangent are almost the same, right? Because we're dealing with small angles, I can express my sine of theta as y over L. Alright? So I'm going to erase this up to this point, and instead of saying sine of theta is equal to s over d, I'll say sine of theta is y over L. I hope you understood this small angle approximation here. We need a space, so I cannot just keep writing. I need to create some space. So we say a sine of theta now is not s over what sine of theta has to be opposite of a hypotenuse. It's not s over d anymore. Rather, it's equal to the tangent of theta, which is the opposite, which is y over the adjacent L. All right. So I'm going to take this expression of sine of theta and plug it in here. So lambda now becomes d times y over L. This is for n equal 1. And remember, at the beginning I told you we were trying to solve for d, which is the distance between the two apertures. So if I make d the subject of my formula, lambda L divided by y should give me d for the double slit experiment. Alright? This is the formula you want to remember. Lambda d is given by d, which is the distance between the apertures of a double slit, is given by the wavelength of your light times the distance between your slits and the screen divided by the distance between the centers of two bright fringes. I want to lay a small bit of emphasis on y. So I'm going to erase this, hoping that you've understood. At least I'm going to erase this drawing and talk a little bit more about y. So usually on the screen, this is what you get. The circles are bright fringes. Alright? So I have my n equals 0 here, n equal 1. Let me write it a little bit bigger. So n equals 0, n equal 1, n equal 2, n equal 1, n equal 2. Then I have dark fringes here. Dark fringes, dark fringes. I had told you earlier that the distance between the center of the fringes, of the bright fringes, is y. So you have y there, another y, another y, another y. Alright? What that means is here I also have a piece of y, which is y over 2. And here I have another piece of y, which is y over 2. In real life, it can be really hard to measure only y. So what you do in order to measure y is you measure multiple bright fringes and you do a division. You find the average. So if I was you, I will not struggle to measure the distance y between just two fringes. What I will do, I will measure these 5 fringes here, right? You have n0, n1, n2, n1, n2. That's 5 fringes. It will give you a certain distance. Let's call that distance x, right? X is for 5 fringes. But how many y's are in x? You have 1, 2, 3, 4, and 5 y's. So I will divide that by 5 in order to know what y is. So if this distance from the end of bright fringe n2 to the end of bright fringe n2 is x, if I divide x by 5, I will get the real distance of y. That makes sense? I hope it does. So what you will do if you were taking an exam, instead of struggling to measure just the distance, the size of one bright fringe, you will measure the size of multiple bright fringes, and you count the number of dark fringes that you have. You have 1, 2, 3, 4. You say 4 plus 1, so you divide your total length by 5. Again, the total distance of these 5 fringes is x. And to find the number I put to divide here, I count the number of dark fringes. I have 1, 2, 3, 4 dark fringes right here, and I divide that by 4 plus 1, which is 5. There are many ways to see this, and when we do the experiment, I will zoom on so you can actually see what we're dealing with. All right? Thank you. So that was the double slit experiment.